Hello everyone, and welcome back. Today we're going to begin our discussion and exploration of the field of elementary number theory. So one of the natural places to start this conversation is, well, what exactly is number theory? So there are a few definitions out there, but I think this one sort of encapsulates the true essence of what number theory is all about, and that is the study of integers, subsets or supersets of integers, other sets of numbers, their structure, properties, and relationship to other sets of numbers. Some people will just define it as the study of integers, but I think it's quite more than that. So let's just introduce or reintroduce or familiarize ourselves with some of the most common sets of numbers that some of you probably have already experienced in other mathematics courses. For example, the set of integers, which is abbreviated by capital letter Z, is the set of numbers or entities, in particular -3, -2, -1, 0, 1, 2, 3, and so on, in both directions. We also have the positive set of natural numbers, some people just call them the set of natural numbers, which is 1, 2, 3, 4, and so on. And if we denote this as n plus, then a natural notation would be, for example, n minus, which is the opposites of the set of natural numbers, which would be -1, -2, -3, -4, and so on in the negative direction. And then the set of whole numbers, which is just fancy set W, which would be 0, 1, 2, 3, 4, which is precisely equal to the set of positive natural numbers unionized with the number 0. So also we can see that the set of integers, Z, can be represented in terms of these sets as well, because therefore Z could be represented as the positive natural numbers, the negative natural numbers, and 0, right? Or you can also represent this as the set of whole numbers unionized with the negative natural numbers. Either one would be perfectly okay. So when we look at this particular decomposition of the set Z, what do we have? Notice that the positive natural numbers, the negative natural numbers, and the number 0 do not have any overlap. In particular, n plus intersection n minus is the empty set. N plus intersection 0 is the empty set, which is why I define it as the positive natural numbers. Some people will just define the set of natural numbers and say, and then they'll argue whether 0 is in that set or not, but I think this is a little bit more nicer. And also we see that the negative natural numbers intersection with the set 0 also is going to be empty as well, right? And they unionize to be equal to Z. So if we look at this, for example, in a Venn diagram perspective, so we have, for example, Z here, we have our 0 set there in the middle, and then on the left-hand side we have, for example, n minus, and on the right-hand side we have n plus. So we practically have a decomposition that does not have any overlap, and every element in Z is contained in exactly one, and at least one, or at most one, of each of these sets. So usually we say that these are what we call partitions. So partitions of the set Z. And when we talk about partitions in general, it has to satisfy two properties: the union of all sets, of all smaller sets, is the larger set, and the intersection, in particular the pairwise intersection, of all smaller sets is empty, or is the empty set. Some people also call those smaller sets pairwise disjoint. Right? So we have the natural numbers positive, the negative natural numbers, and 0 partitioning the set Z, or we have the set of whole numbers and the set of negative natural numbers partition Z as well. So can you think of any other partitions of the set of natural numbers that you probably have encountered in the past? So a very common one, which you probably have encountered when you were very young, is the set of even numbers, which I'll abbreviate by fancy letter E, which is the set of numbers, for example, -6, -4, -2, 0, 2, 4, and 6, i.e. the even integers. And then we have the set O, which is going to represent the odd integers. So this is going to contain, for example, -5, -3, -1, 1, 3, 5, and so on. So this is the set of odd integers. Notice that in this particular scenario, we have two sets that satisfy the union of E and O is equal to the set Z, and E intersection O is equal to the empty set, i.e. a number cannot be both even and odd. So what does that mean in terms of E and O with respect to Z? That means E and O, this set, forms a partition of the set of natural numbers Z. Right? And partitions are going to be very, very useful to us a little bit later on when we start to study the structure of extremely bigger sets, and considering all the elements in that bigger set is sometimes more complicated. So sometimes it's a little bit nicer to analyze the smaller sets that sort of partition that larger set. The next principle that we're going to use to set the stage for a lot of the basic theorems, at least for this introductory video to number theory, is this axiom which states that the set of integers z is going to be closed under ordinary addition and ordinary multiplication. So what exactly does that mean? So that means for all numbers x, y in the set of integers, we have two properties. The addition of two integers will always be an integer, and the multiplication of two integers also will be an integer as well. So we're just going to be taking this as an axiom. If you want to prove this from a little bit more foundational axiomatic set theory, that's more than fine, but it's not I don't think it's appropriate exactly for this conversation. So if the set of integers is closed under addition and multiplication, what type of things can we get out of that? So the first thing that I want to sort of formally define in terms of even and odd is the parity of an integer. So let's assume that n is an arbitrary integer. Then the parity of that number n is a classification. So it's a classification or ability of whether it is even or odd. In some sense, it's the ability of whether that number is divisible by 2 or not. So in terms of this, we're going to define on top of this. So we say that n in the set of integers has even parity. Even parity, some people will just say, or it is even. It is even if there exists some other integer, possibly other integer, k, such that n can be represented as the product of 2 times that arbitrary integer. Else, we say that n has odd parity, or it is odd, simply. Right? So we say that an integer n is even if n can be represented as the product of 2 and some other integer, i.e. n is evenly divisible by 2. And if it's not evenly divisible by 2 and n is an integer, then we're going to say that that integer n is an odd integer. So let's just work through a couple basic proofs of, how to prove that an integer is even and how to prove that an integer is odd. So let's assume that we have 78, which is indeed an integer, and we want to say, okay, is this even or odd? So this integer is even because there exists some integer k, in particular 39, which is indeed an integer, such that 78 can be represented as the product of 2 times that particular integer. In particular, 2 times 39 is equal to 78. Therefore, there exists some integer such that 2 times that integer is equal to 78, which proves that that number 78 is even. So how can we prove that another number, for example, an odd number, is indeed odd? So 41 is not even and hence odd because why? So if we look at the consecutive integers that sort of surround 41, in particular 40 is equal to an even number because it's equal to 2 times 20, so 20 is the magic number that can be represented as the product of 2 and that number to represent 40. And keep in mind that's the unique integer that represents 40. And also we have 42, the next number after the number of integers 41, and 42 is equal to 2 times 21. Right? So 21 is the unique integer that represents 42 and hence makes it even, right? So if there is another integer that sort of represents 41 as an even integer, then it must be equal to the number between 20 and 21. But there is no integer k in between 20 and 21. If we were able to find it, k would be equal to 20 plus 21 over 2, which is not an element of the set of integers, right? And make sure you're not sort of conflating what we're trying to prove and what we're stating here. Keep in mind, we're not looking at 20 plus 21, which is 41, and hence saying that that is not an integer, which it indeed is, but we're saying that this is not divisible by 2, but in particular 21 is not divisible by 2. That's the primary issue with 41 not being divisible by 2, and you can sort of drop this down until you get to the argument 1 is not an even number because 1 is not divisible by 2, and you can sort of force a mathematical induction argument on there if you're not convinced at that stage, right? So since there is no integer between 20 and 21, and the surrounding integers 40 and 42 are indeed themselves even integers, that then forces that 41 is not an even integer, i.e. even and odd integers sort of oscillate every one integer, right? So if that is the case, then we can actually prove a theorem that says something very interesting, right? So if n is an integer that has odd parity, then there exists some integer k in the set of integers such that n can be represented as an even integer plus 1. Right? Because if it oscillates every single integer, even odd, then if you take an even integer and add 1 to it, you should get an odd integer back again. And I sort of invite this to you as a proof because it's actually not too bad to prove on your own. So for example, if we want to use this theorem to prove that 41 is odd, then you can say, okay, 41 is odd because 41 can be represented in the form 2 times some arbitrary integer plus 1. So 20 is the integer that sort of represents 41 as an odd. And you can say that, okay, well, what about minus 34? Is this even or odd? So this is not odd because it is even. And why is it even? It is even since negative 34 can be represented as 2 times some arbitrary other integer minus 17. Right? So that sort of proves how to prove a number is even or odd. Some people will actually just take this theorem as a definition for odd integers, and that's perfectly okay. It really depends on what type of narrative you're trying to set up here. Right? So with these two ideas, there's actually one theorem we get immediately from a comment I made earlier. So for all n in the set of integers, there always exists a k in the set of natural numbers, and in particular this is a unique k, such that n is equal to 2k plus 0, or n is equal to 2k plus 1. And this practically follows the fact that the set of even integers and the set of odd integers partition the set Z, and hence therefore either, if you choose an arbitrary integer, it's either going to be even or odd, right? So here's one question that I sort of want to give you. So question, does Z have closure under plus and times? So we already know that Z does have closure under addition and multiplication. But what about their subsets, in particular the set E and the set O? So is the set of even integers closed under addition and multiplication? Is the set of odd integers closed under addition and multiplication? Let's see if we can establish some basic proofs to sort of explore this particular idea. So the first basic theorem we're going to analyze in terms of closure for the set of even integers is that the set E is closed under ordinary addition. And keep in mind we're going to be taking as an axiom that the set of integers is closed under addition and multiplication, and we're going to see if we can prove that the set of integers is indeed closed under addition as well. Right, so let's see if we can give a nice little proof. So since we're trying to prove that E is closed, we need to choose two arbitrary elements in the set E. So what we're going to do is we're going to choose X, which is going to be 2k1, i.e. this is in the set of even integers. So let's say that that is an element of E. And we're going to choose another integer y, which is going to be equal to 2k2. So it's going to be 2k2, which is of course going to be an element of integers, provided, not if, but where k1 and k2 are some elements z that sort of represent x and y. So what we're going to do is we're going to add these two arbitrary even integers, x plus y, and show that x plus y is also an e. Since x is an e and y is an e, if we can show that x plus y is an e as well, regardless of what x and y were chosen to be, that means e is closed under ordinary addition. So x can be represented as 2k1, y can be represented as 2k2, and notice that since we're working in addition under the set z, it does satisfy the distributive law, so we can factor out a 2 out of this expression, and we're going to have k1 plus k2, and that's due to the distributive law. Keep in mind, the set of integers is closed under addition. K1 is an integer, K2 is an integer, therefore K1 plus K2 is also an integer. So we're going to let K1 plus K2 be equal to K because we know that K is also an integer as well. So if that is the case, we have this is equal to 2K, where K is some arbitrary integer. And since we have that X plus Y is represented as 2 times some other integer, that means this is in the set of even integers, which completes the proof of closure of E under addition. So I invite you to try and see if you can prove, for example, that E is closed under ordinary multiplication. The proof is very, very similar. But instead I'm going to prove another nice little theorem. In particular, the set of odd integers is closed under ordinary multiplication. The set of O is not closed under addition. I invite you to try and find a few counterexamples, or actually prove that the sum of any two odd integers is indeed even, regardless of which two odd integers you choose. Right? So let's see if we can prove that O is closed under times. So what we're going to do is we're going to let x be equal to 2k1 plus 1, and y be equal to 2k2 plus 1, forcing that x and y are both in O, where k1 and k2 are both arbitrary integers in Z. Right? So what we're going to do is we're going to multiply these two odd integers, which is going to be 2k1 plus 1 times 2k2 plus 1. So since we have x's in z and y's in z, and we're multiplying numbers in z, therefore the distributive law is also going to hold for all numbers x and y inside of z. So we can write this as 4k1 k2 plus 2k1 plus 2k2 plus 1 using the double distributive law. What we can do is we can factor by grouping. I'm going to factor a 2 out of the first 3 terms of this expression, and that's going to give me 2 multiplied by 2k1 k2 plus k1 plus k2 plus 1. Now, k1 is an integer, k2 is an integer, k1, k2 is an integer, 2 times an integer is an integer, and the sum of two integers is also an integer. So what we're going to do is we're going to let 2k1, k2 plus k1 plus k2, we're going to represent k because we know that's an integer because z is closed under both addition and subtraction, and also multiplication by 2. Right? So that means this expression is equal to 2 times some arbitrary integer k plus 1, which is the structure of an odd integer, which says that, okay, we've chosen two arbitrary odd integers, we've shown that the product is also an integer, odd integer, and hence O is closed under ordinary multiplication. One big problem that we're going to talk about a lot, especially in the elementary number theory discussion, is the divisibility of integers. So what does it mean when we say that an integer is divisible by something? So the definition says this. We say that an integer is divisible by some number f, and in particular this number has to be an integer, provided that there exists some other integer k such that n can be represented as the product of k and f. In this scenario, we say that f is a factor of n. Hence, or equivalently, f divides evenly into n, right? So let's see if we can work out a couple important theorems or basic theorems associated to the divisibility. So in particular, 1 is a factor of all integers. 1 is a factor of all integers in Z. So, how can we prove that 1 is a factor of all integers? Maybe you want to pause this video and prove it by yourself. So what we can do is we can let n be an arbitrary integer. So since n has been chosen to be an integer, then we can write n to be equal to n times 1, right? So what do we have here? So is 1 a factor of n? That's the question we're trying to answer. And keep in mind n is arbitrary. So 1 is a factor of n if there exists some integer in Z such that n can be represented as the product of that integer and that factor. And we know that n is always equal to n times 1. That's the identity law associated to Z. So therefore, since we have this decomposition, we have exactly what we want, right? So we can see from here, 1 is always a factor of an integer, regardless of what that integer is. Even if that integer is 0, 1, 1 itself, 26, and so on. Right, so that's going to be very important later. So another important theorem is the following. All integers have at least 2 factors. And keep in mind, when we're talking about factors, we're usually talking about integer factors, right? So maybe you want to try and pause this video and prove this on your own. So again, we begin by letting n be an arbitrary integer. And we already know from the previous theorem that one factor of n is always going to be equal to 1, is a factor of n. So what is another factor of n? Also, we can represent n in the following way. N is equal to 1 times n. So what exactly are we claiming here? So we're trying to show that n is a factor of itself, right? So if n is a factor of itself, then there should exist another integer such that our number of interest can be represented as a product of that integer and that conjectured factor, right? So we know that n is equal to 1 times n because in some sense that's a commutative representation of the previous statement, right? But the emphasis is a little different from before because now we're trying to show that n is a factor of itself compared to before where we're trying to show that 1 is a factor of the integer n. Right? So since 1 is indeed an integer, it's the first and least positive natural number, we have, that means the second factor of n can always be equal to n, right? So we have one factor of 1, another factor of n, and you possibly have some others. In particular, you probably even may be curious to show that 1 is the least positive factor of every integer n, and n is always the largest positive factor of an integer number n, which is actually quite useful to know as well. Okay, so let's define a very important class of numbers that people tend to find a lot of interest in. So a positive integer is said to be prime if it only has 2 distinct factors. And from the previous theorem, that means, okay, well, 1 is always a factor, and itself, n, itself, must be the only factors of that particular positive integer. So if 1 and n are the only factors of that integer, then we say that that integer is a prime number, or prime integer, I guess you could say as well. So let's look at a couple examples. So 1 is not prime. So why is 1 not prime? Well, the first factor of 1 is, of course, 1. The second factor, of course, is n, which in this case is 1. And those are the only two factors of 1. But keep in mind, 1 and 1 are not distinct, therefore you cannot count that twice. So since this does not have two distinct factors, this is not a prime number, right? So 1 is not prime solely because of how we define what a prime number is, right? So -1 and 0 are also not prime numbers. So -1 is not a prime number because it's not a positive integer. 0 also is not a prime number because it is also not a prime integer. In particular, prime integers must first be strictly greater than 0. Right? So no negative integers can be prime, 0 cannot be prime, 1 cannot be prime, so therefore all primes must be greater than or equal to 2. So let's look at a few of the numbers greater than or equal to 2 and look at their factors. So let us assume f as a function that produces the factors of a number. In particular, the factors of 2 are going to be equal to 1 and 2. The factors of 3 are going to be 1 and 3. The factors of 4 are going to be 1, 2, and 4. 3 does not divide evenly into 4. The factors of 5 are going to be 1 and 5. Factors of 6 are going to be what? 1, 2, 3, and 6. Factors of 7 are going to be 1 and 7, and you can continue this as long as you want. So notice that we have two factors here, two factors here, two factors here, two factors here. So what does that mean for these things? So 2, 3, 5, 7, you can continue 11, 13, 17, 19, and so on, are all prime numbers, right? And I sort of invite you to sort of say, okay, is there any pattern between all the prime numbers? Maybe, maybe not. We'll see later, right? So to close out this introductory discussion on elementary number theory, and in particular divisibility, prime numbers and divisibility and things like that, let us close off with this very basic theorem. 2 is the only even prime number. So I invite you to try and prove this on your own before I show you how to do it. So let's get right into it. So let us consider, first off, the set S, which is going to be defined to be the positive even integers except for 2, which is going to be the numbers 4, 6, 8, 10, 12, 14, and so on. Right? So what is so special about this set S? Right? So we're not considering this whole entire set E because the negative even integers, including 0, are not going to be prime, so we don't need to consider them, right? And we've already classified 2 as a prime number, therefore we don't need to consider this. So this is the rest of the even positive integers. So is any of them going to be even is the question that we're trying to formally answer, right? But we clearly see that each element of S, each element, let's call each element, arbitrary element, N in S, has two factors, 1 and let's say M, and also 2, because all of these are even, therefore 2 evenly divides all of them, right? So, and also notice that 2 does not belong to the set S, right? But 2 divides all elements of S, right? So that means the factor of some arbitrary element n in S is equal to 1, 2, the number itself, and potentially some others. But notice that this list is strictly more than 2. Strictly more than 2, i.e. the set of factors of n in S is always greater than or equal to 3, right? And in particular, these are all different. 1, 2, and n cannot repeat, right? So since that is the case, that means no other even element in that set S is prime, and therefore 2 is the only even prime number. Quite lonely, but quite useful, right? So those are some of the basics associated to elementary number theory. There are definitely quite a few interesting puzzles and applications that we will discuss, but these are some of the basics just to sort of get your mind working in the realm of elementary number theory. Hope you enjoyed this video, and I'll see you in the next one. Take care.